Hello and welcome to this video lecture on infinite horizon constrained optimal control. Before we start, I would like to remind you that we know of a bunch of ways to solve finite horizon linear-quadratic optimal control problems, but the problem is that the receding horizon control strategy kappa n star can lead to an unstable closed loop system. On the other hand, we can solve infinite horizon linear-quadratic optimal control problems and obtain a stabilizing controller for our linear system. However, if the dynamics is nonlinear, or the cost function is not quadratic, or if we have constraints, we don't know what happens, and we haven't discussed whether the closed loop system with a corresponding controller satisfies the constraints or whether it has any stability properties. This will be the topic of today's lecture. We will state conditions under which the dynamic programming iterates converge, and we will study the stability properties of the controller that we will obtain by solving this infinite horizon problem. But let's first state the problem. Consider this possibly nonlinear dynamical system. Starting from an initial state x0 is equal to x and applying an infinite sequence of inputs denoted by u boldface, we obtain a sequence of states denoted by x boldface. Here xt denotes the state of the system at time t, starting from the initial state x and with the application of the inputs u boldface. The objective is to determine a sequence u boldface star that minimizes the infinite horizon cost v infinity. And v infinity is given by the infinite sum of stage costs, as we see here. The problem needs to be solved subject to certain constraints on the states and inputs of the system. We say that a sequence u boldface is admissible for our optimal control problem with initial condition x0 is equal to x if it leads to the satisfaction of all constraints. The set of all admissible sequences is denoted by u calligraphic infinity of x. This is the set of all sequences u boldface whose elements are drawn from u and starting from the state x will retain all future states inside x forever. U calligraphic infinity is a set-valued mapping. Next, we define the set of feasible states as the domain of u calligraphic infinity. That is, the set of all states such that the corresponding set of admissible sequences is non-empty. But to put it differently, a state x is feasible if we can find at least one infinite sequence of control actions so that all constraints are satisfied. We denote this set by x infinity. Of course, by construction, x infinity is a subset of x. We can now write the optimal control problem as the problem of minimizing the cost function v infinity subject to the sequence of control actions u boldface being admissible. The value function of this problem is defined as the infimum of the cost function subject to the constraints, provided that this infimum exists. This is denoted by v infinity star. We define the solution mapping of the problem to be the set of minimizers, and this is denoted by u infinity star. There is a quite important difference from finite horizon problems which is worth highlighting. The fact that a sequence is admissible does not mean that the cost is defined or finite or that it is finite. Let's see why. Consider this linear system which is not stabilizable and assume that we have no constraints for the sake of simplicity. Regardless of how we choose the sequence of control actions, there is absolutely no way we can make the state converge to zero unless, of course, it is already there. Note that the first coordinate of the system state is independent of the input. Now take this simple cost function. we can see that we cannot make the cost go to zero. So the infinite horizon cost clearly diverges. We see that the fact that u-boldface is admissible does not imply that the infinite horizon cost exists. And the fact that x is a feasible state doesn't mean that it is in the domain of v infinity star. However, in general, we have that the domain of u infinity star is inside the domain of v infinity star, which is inside the domain of u infinity. Hereafter, we shall denote the domain of v infinity star by x infinity star. Under some regularity assumptions, these two sets will be equal. That is, the minimum will always be attained whenever the infimum is finite. We can write the problem using extended real-valued functions so that we don't have to carry the constraints when we apply the dynamic programming method. We define the cost function L bar, which is equal to L plus the indicator of the Cartesian product of x times u. We shall now apply the dynamic programming method and derive Bellman's equation. The value iteration for determining v infinity star is given here. As before, we can start with v0 star equal to 0, for example, and we can apply the dp operator t recursively. The dp operator applied to a function v is defined as the infimum with respect to u of L bar of x comma u plus v of f of x comma u. We can write the dynamic programming recursion without extended real-valued functions as well. For example, suppose that v0 star has a domain x0. Then v1 star is the infimum over u is inside u of the stage cost function L plus v0 star of f of x comma u. And this is defined for x in x1, where x1 is the set of all states x in big X, for which there is a u in u, such that the next state f of x comma u is inside x0. In other words, x1 is the set of all states that can be moved to x0 in just one step without violating any constraints. Recursively, we determine vt plus 1 star from vt star, and vt plus 1 star is defined for x in xt plus 1. The set xt plus 1 is determined recursively from xt. We have defined xt plus 1 to be the set of all states that can be steered into xt in just one step without violating any constraints. Equivalently, we can say that xt is the set of all states which can be steered to x0 in t steps without violating any constraints. Bellman's equation holds for this infinite horizon constraint formulation as well. The proof is shown here, and it is really identical to the one we gave earlier for the case of unconstrained infinite horizon optimal control problems. Here are a few things to have in mind about Bellman's equation and v infinity star. First of all, v infinity star is an extended real-valued function. Bellman's equation is a necessary condition for the optimality of v infinity star. In some cases, Bellman's equation has a unique solution, but not always. Under certain conditions that we will talk about later, the dynamic programming iteration vt plus 1 star is equal to t of vt star converges to the function v infinity star. If the value function iteration converges, then the limit v infinity star satisfies Bellman's equation. There may be other solutions of Bellman's equation that are not equal to v infinity star. Lastly, recall that the domain of v infinity star is a subset of x infinity. Let us now present some very useful results that will help us prove a convergence result for the dynamic programming recursion. Alongside, we will introduce the concept of control invariance. The results of this section will be important for model predictive control. Let's have a look at this result. It says that if we can find an extended real-valued function v such that v is above tv and the minimum is attained at a kappa of x, then the value function of the infinite horizon optimal control problem is bounded above by that function v. Additionally, the infinite horizon cost with that controller kappa is between v infinity star and v. This infinite horizon cost is a measure of the performance of the closed loop system with the controller kappa. This result is exactly what we hoped for, and even more. It establishes an upper bound for v infinity star, and we will be able to combine it with the monotonicity property of t to prove that the value function iteration converges. Let us prove this result first. From equation 2, we have a minimizer of the quantity inside the curly brackets. This is kappa of x. From equation 1, we have that v is above this minimum, which is attained at kappa of x. So we can substitute u equals kappa of x into the right-hand side of this equation. By doing so, we end up with this inequality. V of x is larger than or equal L bar of x comma kappa of x plus v evaluated at f of x comma kappa of x. This holds for all states x at time t, so we can simply replace x by x at time t and rewrite this inequality like this. Next, we can sum up all the stage costs from time 0 to time n-1, where n is just any natural number, and we see that the sum from 0 to n-1 is less than or equal v of x minus v of xn, which is less than or equal v of x. This is simply because v of xn is a non-negative number. And taking n to infinity, we see that the infinite horizon cost is bounded above by v. So we have proven this part of the inequality. By definition, v infinity star is the minimum of the infinite horizon cost function. The sequence of control actions u boldface, which is equal to kappa of x1, and so on, is admissible. Therefore, v infinity star cannot be larger than the infinite sum of stage costs with that control law kappa. And this completes the proof. Note that the control law kappa that we have defined in equation 2 is the minimizer of an optimal control problem with horizon 1. Moreover, this function v is an extended real-valued function. Next, we shall prove an important property of the optimal control law kappa infinity star. Suppose that kappa infinity star is an optimal stationary control law for the infinite horizon optimal control problem. This means that this sequence of inputs is an optimizer of the infinite horizon optimal control problem. To put this differently, this means that u boldface infinity star is an element of u calligraphic infinity star. Then, kappa infinity star is an element of S of v infinity star, that is, kappa infinity star is a minimizer of L bar plus v infinity star of f of x comma u. In other words, an optimal control law, kappa infinity star, is a minimizer of an optimal control problem of horizon 1, with a terminal cost function equal to v infinity star. The proof of this fact hinges on Bellman's equation. Bellman's equation states that this minimum of L bar plus v infinity star at f of x comma u is equal to v infinity star. V infinity star is, by definition, the infinite sum of L bar of xt and kappa infinity star of xt. We can split this sum into L of x comma kappa infinity star of x plus the remaining part from time 1 to infinity. We see now that this sum is v infinity star evaluated at t equals 1, that is f of x comma kappa infinity star of x. Now compare this expression with this one. We see that kappa infinity star is indeed a minimizer, and this completes the proof. The converse is also true. If kappa infinity star is in S v infinity star, that is, if kappa infinity star is a minimizer of this horizon 1 optimal control problem, then it is an optimal stationary control law. To prove this, we will leverage the first result we presented at the beginning of this section. We start with Bellman's equation, from which we have that v infinity star is equal to t of v infinity star. Recall the result on slide 13. We have that v infinity star is an upper bound to t of v infinity star. In fact, the inequality is satisfied as an equality. So using the performance bound result, we have that v infinity star is less than or equal the infinite horizon cost with the controller kappa infinity star, which is less than or equal v infinity star itself. As a result, v infinity star is equal to the infinite horizon cost with the controller kappa infinity star. And this means that kappa infinity star is an optimal stationary control law. We conclude that the sequence of control actions u boldface infinity star produced by a stationary control law kappa infinity star is optimal if and only if kappa infinity star is in S of v infinity star. To put it differently, this means that a stationary policy suffices to achieve optimality, and that if we have v infinity star, we can determine an optimal stationary control law kappa infinity star by solving an optimal control problem of horizon 1. Let's go back for a moment to have a look at this result. We have proven that if the extended real-valued function v is larger than or equal tv and kappa is inside sv, then v infinity star does not exceed the infinite horizon cost of the system with the controller kappa, which does not exceed v. Of course, if v is equal to tv, that is, if v satisfies Bellman's equation, this result still holds. We have also shown that v infinity star satisfies Bellman's equation. Conversely, if v is a fixed point of t, that is, if v is equal to tv, then v infinity star is below v. This means that v infinity star is the smallest fixed point of t. Now we will introduce the concept of control invariance. Consider this possibly non-linear dynamical system, which is subject to the constraints xt is in x and ut is in u. A subset of x, let's say a set A, is said to be control invariant for this system if for any x inside A, there is a control action u taken from u such that the next state, f of x, u, is again inside A. In other words, a set A is control invariant if whenever we start from inside A, there is a control action drawn from u that keeps the state inside A. Now have a look at this. If v is an extended real-valued function that satisfies the inequality v is above tv, and the minimum in this expression is attained, then the domain of v is a control invariant set. The proof is quite straightforward, so take a point x in the domain of v. We need to show that there is a control action u in u such that f of x, u is again inside the domain of v. Equivalently, we want to show that v of f of x, u is less than infinity. Indeed, since x is in the domain of v, v of x is finite, and it is also above tv. Since the minimum is attained, we can see that there is a u star in u such that v of f of x comma u star is finite, and this really completes the proof. We can now state certain conditions under which the dynamic programming recursion converges to the infinite horizon value function. Firstly, we need to state 4 regularity assumptions. These are that the stage cost is a continuous function, the system dynamics f is a continuous function, the sets of constraints x and u are closed, and either u is a compact set or L is above a k-infinity class function of the norm of u. In other words, the growth of L is controlled by the norm of u. Let us now state this dynamic programming convergence result. Suppose that we have a sequence of dynamic programming iterates where v0 star is equal to a continuous function vf plus the indicator of a closed set xf. Suppose also that the regularity assumptions are satisfied. Then if we can choose v0 star so that it is below v infinity star, the limit of the dynamic programming iterates will be equal to v infinity star. Moreover, the minimum in Bellman's equation is attained and the domain of u infinity star is equal to the domain of v infinity star, which is denoted by x infinity star. According to this theorem, starting with a v0 star that is a lower bound to v infinity star, the value iteration converges to v infinity star. We can choose v0 star to be the indicator of x, that is, vf can be taken to be equal to 0 and xf can be taken to be equal to x. We will now show that kappa infinity star has some favorable properties related to stability and invariance. Recall that if we solve a finite horizon optimal control problem, even a linear quadratic one, and we obtain a receding horizon controller kappa n star, the closed loop system will not necessarily be stable. However, the controller kappa infinity star that we obtain by solving an infinite horizon linear quadratic optimal control problem is a stabilizing controller for the associated linear system. The question is whether the origin is attractive or asymptotically stable for the kappa infinity star controlled system over the domain of v infinity star. But there is a more important question that has to do with the constraints. The controller kappa infinity star is defined over x infinity star. Only if our state is inside x infinity star can the controller be used. We wouldn't want the controller itself to lead the state outside of x infinity star. Because if this happens, then the system would immediately fail. The controller wouldn't be able to provide the control action. So we ask whether x infinity star is positive invariant for the kappa infinity star controlled system. And thankfully, the answer to this question is positive. Indeed, under the regularity assumptions, the set x infinity star is positive invariant for the kappa infinity star controlled system. That is, for this system. To prove this, we need to show that if x is inside x infinity star, then f of x comma kappa infinity star of x is also inside x infinity star. We start by taking a point x in x infinity star, which is the domain of v infinity star. This means that x is in the domain of t v infinity star, which is the same function by Bellman's equation. And we rewrite this using the definition of t. Since the regularity assumptions are satisfied, the minimum is attained at kappa infinity star, so we can plug in kappa infinity star and get rid of the minimum. Now this implies that f of x comma kappa infinity star of x must be in the domain of v infinity star. And this completes the proof. This property is known as recursive feasibility. So once we are inside x infinity star, we will remain inside x infinity star forever. Next, we want to show that the origin of the kappa infinity star controlled system is attractive over the invariant set x infinity star. To that end, we will use Lyapunov's attractivity theorem, which states that if there is a non-negative valued function v and a k infinity class function alpha, such that the Lyapunov decrease condition is satisfied over some set x, then the origin is globally attractive over the set x. The idea is to use v infinity star as a Lyapunov function. So consider the kappa infinity star controlled system. From Bellman's equation, we have this expression where we see the difference of the energy of the controlled system at the next state minus the energy at the current state. Clearly, it suffices to assume that L of x, u is larger than or equal some k infinity class function alpha L of the norm of x. This leads naturally to the following three assumptions. These are known as the attractivity assumptions. The first one is that the origin is an equilibrium point of the system. The second one is that x and u contain the origin. And thirdly, that the stage cost at the origin is equal to 0, and there is a k infinity class function alpha L, such that the stage cost L of x, u is above alpha L of the norm of x, so that the stage cost is controlled by the norm of x. As an example, we can take the stage cost to be a quadratic function of the form 1/2 x transpose qx plus u transpose ru, where both q and r are positive definite matrices. And in that case, we can take alpha L to be 1/2 times the minimum eigenvalue of q times s squared. So we have the attractivity theorem that states, suppose that the regularity and attractivity assumptions hold, then the origin is attractive for the kappa infinity star controlled system, which is this one shown here. So it is attractive over the positive invariant set x infinity star. So we have stated conditions under which the origin is globally attractive for the controlled system over x infinity star, and we did so by using v infinity star as a Lyapunov function. We shall now try to see whether the origin is globally asymptotically stable over x infinity star. Recall Lyapunov's stability theorem. It states that if we can find a function v which satisfies Lyapunov's decrease condition, a global lower bound and a local upper bound, then the origin is globally asymptotically stable over a set x. We have already proven Lyapunov's decrease condition for v infinity star. The global lower bound is easy to show for v infinity star. V infinity star is the infinite sum of non-negative stage costs. Naturally, it is larger than or equal the first stage cost, which has been assumed to be above a k infinity class function alpha L. In order to have global asymptotic stability, the local upper bound needs to be satisfied as well. We must assume there is a k infinity class function, let's say alpha over line, and a positive number r such that v infinity star of x is less than or equal that alpha over line of the norm of x for all x in the intersection of x infinity star with a ball of radius r. This holds if there is an admissible sequence of inputs u bold face and the positive number r such that the infinite horizon cost is bounded above by alpha overlined of the norm of x for all x in that set. This is because v infinity star is below the infinite horizon cost of u bold face. So we have proven this stability result. If the regularity and attractivity assumptions hold and there is an infinite sequence of control actions u bold face taken from u infinity, and there is a positive number r such that the infinite horizon cost that corresponds to u bold face is bounded above by alpha overlined of the norm of x, then the origin is globally asymptotically stable for the kappa infinity star controlled system. We see that attractivity was easy to show, but global asymptotic stability was more difficult. So often we will have to be content with attractivity, but not asymptotic stability. The infinite horizon optimal control problem yields the best controller we can obtain for a system. However, in most cases, we cannot compute kappa infinity star. MPC is a finite horizon approximation of the infinite horizon optimal control problem, which retains its stability properties. And with this, we conclude today's lecture. Thank you very much for watching, and I'll see you in the next video on MPC.